Hello everyone. This is the presentation of the paper on landmark distances in polygons, and it's joint work with Craig Goldsman from the New Jersey Institute of Technology and myself. I'm Kai Hormann from the Università della Svizzera Italiana in Lugano. It happened so that we just moved into a new building last year, and I still have problems finding my way around. So at blue dot, that's my office, and that's the bathroom. And I really have trouble finding my way. Well, that is because it's indoors. If it were outdoors, I would have no problems because, as every other Swiss, I go to the mountains very often, and in the mountains I know very well how to orient myself. In particular, I know that when I'm on a mountain and I want to go down, I can simply go always in the direction of steepest descent. And I know that if I do this, then eventually I will end up probably back at my car. More formally, this is a method that was first suggested by Cauchy in 1847, and suppose you have a height function or another two-dimensional function, scalar function, then if you define the gradient at some point and you simply walk a little bit, this is the scalar lambda n, a little bit into the direction of the negative gradient, then it is sure that if you walk just not too much, then you will go down. And this creates what's called a gradient descent path. So x0 is the initial point, and then you go to x1 and x2 and so forth, and that will surely lead you to a minimum of this function h. Now, what if the corridors and rooms of our floor are a polygon P, and the bathroom is just a target point inside this polygon, and suppose we also had a function h sub t with a unique minimum at t? Well, if we add all that, then I could get from my office to the bathroom the way I like it, by gradient descent. And not only myself, but actually everybody else could get from any source S inside P to T by gradient descent. And that's what we want. Now, how to do this in practice? Well, if the polygon happens to be convex, then it's very simple, because we can take as such a function just simply the Euclidean distance function from T inside the polygon. So if we do that, then the contour lines of this function look like this. Of course, it increases radially with gradient 1 away from t. And if we are at some s and follow the gradient path, then that gives us just the straight line segment from s directly to t. Now that's great for convex polygons, but if the polygon is non-convex, then this leads to local minima where you can get stuck. Because if we look at the Euclidean distance function for this non-convex polygon, and we happen to start here, and we walk down by gradient descent, then we hit the boundary, and even if we modify the method and then take the restricted gradient along the boundary, we still end up in a local minimum where we get stuck and we can't go on anymore. Now, the right thing to do in a non-convex polygon is, of course, to take, instead of the Euclidean distance, the geodesic distance from t. Now, that measures the length of the shortest path from x to t within P, not just in the Euclidean sense, but within the polygon. And if you now start at some s and you follow the geodesic distance by gradient descent, then you're sure to arrive at t again, and you even recover this shortest path inside the polygon. Now that's great. It's a perfect means to get from any source S to any target T by gradient descent inside any arbitrary non-convex polygon, but there are a few buts. So first of all, you need to compute, in order to compute this geodesic distance, you need the visibility graph of P. Or to be more precise, you even need the visibility graph of P and the points S and T. So that's all the edges that connect the vertices with each other without obstruction. But that's quite costly, O of n squared log n, if you have n vertices. And it creates O of n squared edges. And if you then find the shortest path, say with Dijkstra, then it's still an O of n squared log n operation. So that's quite costly. Sure, if n is small, then it's not a big deal. But what's even worse is that this requires global knowledge of the domain P. And I'm getting old. I can't remember the whole floor plan. So this is not how I can get to the bathroom. So can we devise maybe a local method that really requires only some local knowledge of the domain and still gets us to the target? Answer is yes. And what we need is the landmark distance. So what's that? Well, it's one way of approximating kind of the geodesic distance, and the idea is to measure the distances to certain landmarks. So landmark, we place them usually just at the vertices of the polygon. And so in order to define now the landmark distance, we first measure the distances to this landmark inside the polygon? Well, in the convex case, that's just Euclidean distance. So here's the distance from x to the landmark Li, and here's the distance from t. And now we construct these so-called landmark functions, which are just the absolute value of the difference of these distances. T is fixed, so that's a function of x. Now, in this situation, for this landmark, the difference is basically 0, so that's certainly not a good approximation of the distance between x and t. But for other vertices of the polygon, say the landmark over here, you can see that the difference of the distances of t and x to that Lj are now starting to get quite close to the distance between x and t. And if we then take the maximum of all these landmark functions, one for each vertex of the polygon, then that defines the landmark distance, and that in the end turns out to be a pretty good approximation of the geodesic distance between any 2 points, and not only in a convex but also in a concave polygon. Now let's study first these landmark functions a little bit more. So that's the definition: distance from x to the landmark and from t to the landmark, difference in absolute value. So you can think of it 1D analog like this. This is the geodesic distance from any x to the landmark Li. Now we shift that by the distance between t and Li, and we take the absolute value. So this is how it looks. At Li, we have local maximum, then it goes down with descent gradient 1 down to t, where we have 0, and then it goes up again. Now in the 2D setting, it more looks like this. So here the contour lines of the landmark, the orange landmark Li, they look really just like the contour lines of the geodesic distance, only that it's a bit modified, as you see in the 1D example. So it first goes down until it hits the 0 contour line that goes through t, and then it goes up again. Of course, by definition, this is clearly a non-negative function. I already said it has 0 contour running through the target t, and it also, one can show, it has a local maximum at the landmark itself. But the gradients, well, the gradients, they have always unit length because it's just basically a shifted and absolute valued geodesic distance function, and it is pointing away or towards Li, of course, in a geodesic sense. So in the region between Li and the 0 contour, the gradient is pointing towards Li. Now in the image, you see the negative gradient because we use that for the gradient descent. That's pointing away from Li. And beyond the 0 contour line, it's always pointing the negative gradient towards Li. And even here, it's pointing towards Li because it's pointing towards Li inside the polygon. So that's the shape of these landmark functions. Now the landmark distance, that's the maximum of all these landmark functions. And it looks like this, the contour lines. So t is the target here or there, and you see it grows away from t, and it clearly is a non-negative function by definition because the lambda i's are non-negative, and it also clearly has a global minimum at t because that's where all these landmark functions, the lambda i's, are 0, and so you have this global minimum at t, that's for sure. One can also show, that's basically following from the triangle inequality, that it's bounded by the geodesic distance from above, and we have equality exactly when t, the point x, and some landmark Li are co-geodesic. Remember this, we'll get to that, back to that at the end of the presentation. Now, the landmark distance, therefore, is a perfect means to get from any s to any t by, in the discrete setting, by greedy routing. That's a very simple algorithm to get to t in a discretized domain. So if we polygonize or we triangulate our domain and we then compute the landmark coordinates, that is the landmark distance for any vertex x of this triangulation to all the landmarks, all the vertices of this polygon, we compute this distance, put them in a vector, and these are stored. Now we have those available now at every point. And then if we want to really route, if we want to get to the target, all we have to do is to evaluate the landmark distance. That is basically just the maximum norm of the difference between the landmark coordinate vector at the current point and the landmark coordinate vector at the target. And that can, of course, be computed simply in O of n, and it's a completely local operation. That's important. And now the routing itself works like this. You simply compute then the landmark distance at all the neighbors, and you go to the neighbor that has the smallest landmark distance. That still is a local operation, gets by with local knowledge, and the complexity is still O of n if n is the number of landmarks. And that happens to work pretty well. As you can see, these are all the paths that go from all the points of the triangulation to the target. And they're pretty good when it comes to comparing them to the shortest path. Now in the continuous setting, it looks like this. So here you see that the paths are now just inside the domain, and again arriving at t. So these are really the gradient descent paths in the continuous setting, and they are not too bad, pretty close to the shortest distance paths. And you may ask, what is this color coding that we have here in the two plots? Well, that is, we need a definition for that. So we say that the landmark distance is determined by one landmark Li if that is the one that wins the maximum competition that defines the landmark distance. So if lambda I for some I is equal to lambda t, we say the landmark Li determines the landmark distance. And here we have simply colored the vertex or the interior of the polygon according to the landmark that determines the point, or the landmark distance at a point. Now you see that most points inside the polygon are really uniquely determined by just one and exactly one landmark. And if we group those that are determined by the same landmark together into regions, and we take the closure, then we have what we call the regions of the landmark partition. It's kind of similar to a Voronoi partition of some domain, but different, of course, but similar. And so, for example, here the orange region, that is the region corresponding to this orange landmark. So all the points that are uniquely determined by this landmark are here in this orange region. Now, we can show that the boundaries of these regions are elliptical and hyperbolic arcs, and not only in the convex, but also in the non-convex setting. And inside each of these regions, of course, we have no problem, because inside the region, since the landmark distance function is equal to the landmark function, then the gradient is also just the gradient of the landmark function within this region. And we already learned that that's just a straight line pointing away or towards the corresponding landmark. So that explains why here inside the regions you see these straight lines. Now they at some point hit the boundary, of course. And the big question just remains, what happens at the boundaries? Well, at the boundaries we have points that are determined not by one landmark, but by two simultaneously, or even three sometimes. And the big question is now at the boundary, where the gradient of the landmark distance function is not even well defined because we have a C1 discontinuity there. We can show that there still is a direction of steepest descent, so you cannot be stuck in a local minimum there. And that direction actually happens to be along the boundary itself, and that explains what you see in the picture, and it always routes you, gets you closer to T. Now, in order to understand this a little bit better, let's take a second look at these landmark functions and assume for the moment that S and T are fixed. Now, if we consider now all the positions where a landmark could be to deliver the same landmark function value. So suppose we have a landmark here and the landmark there and the landmark here, and not necessarily on the boundary or at the vertices, but just somewhere. And now you can compute, of course, a landmark function for each of these landmarks. And suppose they all give a constant value. Then you can figure out quite easily that they must lie on a hyperbola with foci at S and T. And it's also quite easy to understand that if you widen this hyperbola and consider all the landmarks on this green hyperbola, they will have a smaller landmark function value, while if you tighten the hyperbola, then you will get larger, bigger landmark function values. Now, if you put this together with the definition of the landmark distance as the maximum of all the lambda i's for landmarks at the vertices, you understand that the landmark distance at S for T, for some fixed target T, is corresponding to the tightest hyperbola with foci S and T that contains at least one vertex, one landmark at the vertices of the polygon. Because if it were tighter, it wouldn't contain the landmark anymore, so that function is not available among all the landmark functions. That function, well, if you make it larger, then you make the value smaller. So the landmark that sits on the tightest hyperbola, that is the one that determines, or in this case, even co-determines the landmark distance. So you have two, the yellow and the cyan one. And since this hyperbola intersects the boundary in at most 4 places, we will have at most 4 co-determining landmarks for any point inside the polygon. And it happens so that the gradients of these co-determining landmarks, maximally 4, that they are always aligned. We can show that in the paper. And so since they are aligned, meaning that they point basically in a similar direction, so they are on one side of some half plane through the point S, there is always a direction of steepest descent, a direction in which all the co-determining landmark functions decrease, and therefore also the maximum, the landmark distance decreases. And that's how we can get on even if we are on the boundary. And that then shows that we have for sure no local minima on the boundary, and therefore we have no local minima anywhere. And that's the bottom line, the conclusion of the whole thing. The landmark distance function that's based on the vertices of P, so landmarks at the vertices of P, has a unique global minimum T and no other local minima anywhere inside the domain, and therefore it can be used to get to the target by gradient descent. So for any fixed T and any variable S inside the domain, gradient descent, or rather steepest descent, because the gradient may not be well defined, but steepest descent always is guaranteed to lead you to the target. We proved this in the paper for the continuous setting, very in much detail, and we also observed and conjectured it for the discrete setting, where we ran a lot of examples and it always worked out nicely. But it still needs to be proven in the discrete setting. It's also very crucial that you put the landmarks at the vertices of P. In previous papers, that was not always the case, but if you put them anywhere else, for example, in the interior, then this may lead to local minima of the landmark distance function, and that's where you can get stuck if you go down by steepest descent. And another nice feature, and that goes back to what I mentioned before, is that if you add more landmarks on the boundary of the polygon, then the landmark distance function starts to converge to the geodesic distance function, which is an upper bound always. But in the limit, it approaches this upper bound. And that goes back to this property that I said, that if the target T, some point X, and some landmark are co-geodesic, then the landmark distance is equal to the geodesic distance function. And as the landmarks become denser and denser on the boundary, then for any S inside, there will always be a corresponding landmark on the boundary such that S, T, and the landmark are co-geodesic. And that's why you reproduce the geodesic distance in limit. That's all, folks. For more details, I'll refer to the paper, and I thank you for your attention.